Okay, and we have an explicit formula, okay, for the distribution or the density matrix of a system coupled to an external environment, where the external environment is determined by this parameter, which is known as the temperature. Okay, and that's a mixed state. It's a mixed state. It's very far from a pure state. Okay. That's why we have the next slide. Okay. So
Can you repeat the question?
What is Z? Don't worry, I'll define Z. Okay. It's a real number. Yes. In a second. Wait a second. So up to this coefficient, okay, the density matrix again is a matrix. We exponentiate our Hamiltonian and we multiply it by a factor which is known as beta, okay, and beta is just 1 over the temperature, okay. This value here, KB, is known as the Boltzmann constant. It just fixes the units, okay. If you want to measure, yes.
What's a unitary operator?
It's not a unitary operator. There's no I. There's no I. There's no I. Okay, so I have to say, in regards to unitary, it has an intimate tie with the unitary operator we've seen before. If you complexify the temperature, it would precisely give you that. Okay, that's a good point. Okay, okay.
But the reason it's a density matrix.
You're telling all the secrets. So
The reason it's a density matrix is just do a Taylor expansion, and then you get a. I mean, H is a positive semi-definite,
Yeah.
positive matrix.
It's a positive
so
semi-definite.
it's some
Okay.
combinations of H, H squared, etc. So it's a density matrix.
Okay, so yeah, so
Yes.
we need to normalize it, and this is what Z is for. Okay, so we need to normalize everything. So Z is just the trace of this object, and written in terms of the eigen values, it's a sum over e to the minus beta of all the eigenvalues. Okay, so Z is just a normalization constant, which is actually not very easy to compute. Okay, if you can compute Z, you can tell a lot about the system, but for this case, it's just a normalization constant. So let's try to get some intuition of how this object behaves like. Okay, so we can take 2 limiting cases. So let's, yes, ask, yes.
What is the temperature? What parameter is the T?
This one, T is the temperature.
T is the temperature.
Yes.
Right.
So this is quite.
And all the rest are constants. Okay.
All the rest, okay. So the Hamiltonian, you know, it can depend on many parameters. That's
so
your
if
system.
the temperature is infinity, this is e to the I, e to the minus I,
E to the 0,
e to the
0, which is 1,
e to the 0, which is I. I see. So you
which
get
is 1.
You get the completely mixed state.
Right, precisely.
That
Precisely. Okay. So when as was mentioned here, when the temperature goes to infinity, all the states are equally probable. Okay, there's no preferential to any energy eigenstates. Okay. On the other hand, as you lower the temperature, okay, so when T goes to 0, beta goes to infinity. So here actually the density matrix acts as a projector. Okay. It projects to the ground state. It would prefer states with a lower energy. Okay, it gives you a hierarchy of how abundant different energy states are. Okay, lower energy states are preferred, higher energy states are not preferred. Okay, so that's a very important density matrix that we use quite a bit. Okay. Okay. For the interest of time, should I skip approaching equilibrium or not? Not. Okay. So that's a huge topic of its own. You can spend a few classes on that too. But the question, how does the system reaches equilibrium? Okay, so when you enter the room from the outside, it wasn't that hot, but it was hotter than the air conditioning here. So there was a time period when you had to relax or to approach or equilibrate with the temperature which is dictated by the air conditioning here. Okay, and so how do you model this? Okay? So there are many ways to model this. Okay? And I try to give you one point of view. This point of view is a classical point of view. There's a generalization to this which involves quantum mechanics, but again, it's too involved. I try to give you some intuition how this happens classically. Okay? So the way to think about it, we said that the environment and your body here exchange energy. Okay? Your quantum computer would exchange energy with surrounding. So you can think that they're like random energy depositions that go into the system. The system can sometimes absorb energy from its environment and sometimes can emit energy from its environment. There are fluctuations. It's a random variable that can fluctuate in time. And the most natural way to describe this, again for mathematics, is known as the Markov chain. Okay? And maybe the process to think about is the following thing. Okay? So suppose you have your classical bit state. Okay? I wrote qubit, so it's everything would be classical here, so you can erase this. Okay? So it's a classical bit state. So you have a string of zeros and one. Okay? And now, each time, some molecule comes from the environment and induces a bit flip. Like we learned yesterday, you apply the X operator, the bit flips. Okay? So when you wrote this down, you didn't take into account the Hamiltonian, because we didn't learn about the Hamiltonian yet, right? So there were no energy considerations. Okay? But any incident of a bit flip can, in principle, induce some energy penalty. It might be that when you flip the spin, the energy increases or decreases. Okay? So in order to capture this, we write down those transition rates. Okay? It tells you what is the probability for the bit to flip. Okay? So we can think about a process where we have some given initial condition with a bit 0 here, and another state where the bit was flipped. And we can think that we sort of go between those states, okay, sequentially at each time. And this follows some rate or probability for this thing to happen, okay? So how all of this is related to temperature, okay? So it turns out that, if you make a specific choice for those rates, okay, this is known as a detailed balance condition, okay? You're guaranteed, that's a mathematical theorem, okay? You guarantee that after a long time evolution, you reach some equilibrium state, okay, where the probability distribution would not change in time. This is when we settle to this Gibbs state. And we need to choose a specific ratio of those rates, okay? And this specific ratio is given by the Gibbs distribution. Okay? Now, yes. So it's the equilibrium distribution. Okay? So the ratio between those two should be e to the minus beta, the energy difference between those two states. Okay, in the quantum mechanical setting, it's slightly more involved. I didn't want to go with this. It's a Lindbladian equation. It's involved. I'm just giving you the sort of the classical equilibrium process for a classical bit, not a quantum bit. Okay?
This is the left eigenvector that corresponds to
Precisely.
That corresponds to what?
Yeah. Yeah. According to the Frobenius theorem, you can. Okay. Good. So you see there's some arbitrariness on the choice of those W's. There are many W's that would satisfy this. A common choice is known as the metropolis dynamics, okay, which goes as follows. You suggest to flip a spin, and now you check what is the energy cost of flipping the specific spin, and now you have two options. You either accept or reject this move. If in the metropolis dynamics, if the energy decreases, you say, great, I want to lower the energy. I'm always accepting this. If the energy increases, now you toss a coin, and and you accept it with probability e to the minus beta delta e. Okay? So I ran a simulation, and this was the result of the simulation. So what is plotted here? Okay, so we think about a single bit coupled to its environment, And we start with some initial state, which is far from the equilibrium dictated by the environment, okay? So you should think about, you entered the room, your body was at a higher temperature than the environment here, okay? So this is what you hear. And then there would be a relaxation process, okay, with some time scale, known as the thermalization time, after which you would reach your equilibrium, and the equilibrium is not dead. That's maybe something I want to emphasize. The expectation value would be the thermal expectation value, but there would be fluctuations about this, and the fluctuations are dictated by the temperature, the specific heat, and and many other physical concepts. Yes.
Maybe I lost you a bit, but
Sure.
like the evolution, what is changing over time again? Like the state, is it quantum here or not?
The probability distribution changes with time of a bit. Okay, so remember in the model of computing in the first lecture, so we had two options. We have bits and qubits. Okay, and the bits were described as some probability distribution, p up and p down. Okay, and this probability distribution changes with time.
Maybe a bit of a clarification. There were sort of two different types of ways we talked about Hamiltonian. The first one was about dynamics, that we started from a pure state, let the state evolve by the Schrödinger's equation. And that's sort of, there's no bath, there's no thermal nothing, there's no interaction with the environment, it's all unitary, that's it. And then what Snir is talking about now, so in the previous few slides about the equilibrium, he was talking about a different thing.
Right.
Given a Hamiltonian, a fixed Hamiltonian, you wait for infinitely long, never mind how long, and there is an equilibrium state called the Gibbs state. And now, this is a confusing thing. Now he was talking about how the system evolves to that equilibrium state, and this is no longer unitary dynamics. This is dynamics that is non-unitary. It's not that you start.
Right.
You could start from a pure state and then you evolve to
Into a
the
mixed
Gibbs
state,
state, and
yeah.
that the dynamics involves what Snir talked about, a bath, or you can think about it like a metropolis process that changes the state randomly, and then it evolves to that Gibbs state.
So are we from the top, because we know at the end we'll get to the Gibbs state, the points in the graph that we have the Markov chain on are the eigen vectors, like the eigen
Okay,
waves?
so
No,
what
it's
I-
not.
what I-
so
okay,
why
so-
do we have
So yes
finite?
and no. Okay.
Yes and
so the no part is that in the last two slides, actually, I did not discuss quantum mechanics. Okay, it was a bit mechanics. Okay, the quantum mechanical analog of this is even more complicated. What you need to do, you will need to write down an analog for the Schrödinger equation, but for the density matrix. It's known as Lindblad dynamics. It would take me a few hours to explain. Okay, so I scaled this down. Okay, and I discussed bit dynamics. Okay. And what are in those blobs, okay, are different bit states or different strings of zeros and ones, okay? The system can start move between them.
Although we're not in quantum, we still take as a hypothesis or something that it
Yes,
evolves.
this is my model.
So,
okay.
so what is the model?
The
exactly?
model is that-
what is the dynamic? Like what governs
Okay, so what governs the dynamics?
the W? You just
W.
the
W
W
governs the dynamics.
Can you go back so
Yes.
that we can see?
W is the transition
Yeah.
rate between the different blobs in the Markov chain.
So W is a stochastic matrix determining the stochastic process
Exactly.
with this condition, detailed
Right.
balance.
So what I want to tell you that the important bit of information is that if you choose your stochastic matrix, as you said, to obey this detailed balance condition,
Yes.
I can assure you that if you wait long enough, okay, the end distribution that your bits would reach would be governed by a Gibbs distribution. Okay, that's a theorem.
Wait,
Okay.
Gibbs. Oh, you
E
mean
to the minus
you mean
beta.
classical statistic mechanical Gibbs,
Right.
not
Right,
okay.
yeah. And if you want to generalize to quantums, there's a quantum generalization of that, where instead of the instead of the probability distribution goes as e to the minus beta e, the density matrix that describes the state would go to e to the minus beta h as an operator. Okay, but
Wonderful,
that's
thanks.
even more
thank you.
involved. Okay, hopefully, yes.
When
Yes.
we reach W, are we just in a standard Markov chain problem or the directed graph, a reversible Markov chain?
Again, what do you say? What's the question? How do you compute
So
W? or
no, when we reduce to W, suppose we know W. W is governed by some energies, whatever.
Yes.
But once we know W, it's just a standard Markov chain. problem.
Exactly. Yeah.
I suggest.
Okay, let's move on.
Is it absolutely important?
Okay, now I would like to give an example for a thermal density matrix. Finally, see here I was fine. I wrote qubit everything. So let's try to compute the thermal density matrix of a qubit in an external field. Okay, so precisely like before, we have the same Hamiltonian. It's minus hz times z. Okay, hz replaces h bar omega over 2. It also has units of energy. And it's a very simple Hamiltonian. And because it's already diagonal, it's very easy to exponentiate. Okay, and the thermal state that you would reach is the following thermal state. Okay, with this normalization. And we can, for instance, measure the magnetization. What is the magnetization? It's the expectation value of z. It tells you how much up do we have and how much down, where we think about up as 0 and down as 1. And simple algebra, which I encourage you to do, give you the hyperbolic tangent of beta z. So let's try to understand what does it mean. So here, let's take the limiting cases. So here I plotted the expectation value of z as a function of the temperature. Okay? So let's first go to 0 temperature. So what I told you about 0 temperature, here, when we take 0 temperature, the thermal density matrix acts as a projector. It would project to the ground state. And we know what is the state of the ground state. What is the ground state here? This one. Okay, it's the lower energy state. Okay, so here the spin is fully polarized. Okay, it points precisely in the 0 direction. Okay, so we get 1. Now if we increase the temperature, all states are probable. Okay, and indeed as we go to infinite temperature, the expectation value of z goes to 0. Okay? So remember this, it would pop up later on. Okay? I encourage you to do this. Very simple exercise, explains most of the things. Okay. So now it's a good time to take questions because I'm moving to, I think the more interesting part, but yes, it's the equilibrium state. I'm not talking about how I reach the equilibrium state. This would be the equilibrium state.
So, what position was before, and you say after everything that you did, that you go up, you agree with something down, you always agree. At the end, you end up with no thermal.
Right.
And the question is, you always have no thermal.
If you would obey detailed balance, there's some more technical thing about ergodicity, but you can, there's a bunch of important math. But in general, for a non-contrived problem, if you follow detailed balance, you would end up in a Gibbs distribution.
Snir, in the interest of time, I think since we do want to hear something about phase transitions towards tomorrow, maybe
Okay,
maybe you
let's start.
progress a little bit and
Yeah.
then again
Okay.
question.
Good. Okay, so this is a philosophical slide, which I think is important because it would sort of lay out the map of what I will do later on. Okay, so what do we do in condensed matter? We take a piece of material, it's a magnet, and since it's a quantum meeting, nowadays you don't need to look up for materials. You can quantum engineer them. We have amazing platforms, superconducting qubits, cold atom, trap ions. You can engineer amazing Hamiltonians, and this is a huge revolution. And okay, so we have our piece of material, and what do we do? Okay, so you take a magnet and you start to probe it. You try to understand what are the properties of this material. And what we end up doing, if you open any paper in material science on condensed matter, you typically see this diagram here, which is known as the phase diagram. Okay, what this phase diagram tells you, it tells you the following thing. So as a function of parameters, for instance, the strength of the field here induced by this external probe, or the temperature, you can heat up the system or cool it down, you would end up having regions in space which have a sharply distinct behavior. Okay? You can end up in a region in states which I called here a ferromagnet. I'll explain that all, where the magnet magnetizes. Okay, it exerts some magnetic field. You can end up in a region in space where it's a paramagnet. It's no longer a magnet. And there's some crazy states like spin liquids, which we actually already seen. The toric code is a spin liquid. Okay, you can end up in a state which actually does not magnetize even in zero temperature. H is the external magnetic field exerted by this. You see, I download this nice magnet, and this is the strength of the magnet is H. Okay, yes.
So H is the property of the material, or T is the property of the
No. H and T are external parameters that change in an experiment. Okay, so you have a knob in the experiment. Okay, you can control the temperature, you control the strength of the external magnetic field. As a function of those parameters, the material would behave differently. Okay, so the kitchen example, you take you put water in the refrigerator, you get an ice cube. That's one phase. You take them out of the refrigerator, you put them, and you wait until the relaxation time is over, and you get water. And that's a different phase of matter. Okay, so you can think about a ferromagnet and paramagnet, let's say ice and water. Okay, and it generalizes to many other materials, etc. Okay, good. And the last bit, which interests me the most, I'm not sure if we reached to it. The phase transition itself has very interesting properties. In particular, it displays what is known as a universal behavior, which is insensitive to the material itself. And this is one of the triumphs of condensed matter. Hopefully, I'll reach this point at the very end. Okay? Okay, so I laid out.
Maybe just to say,
Yeah.
this is called a phase diagram. So a phase diagram means it's not, the graph is missing another dimension, which is something that corresponds to what is a ferromagnet, what
Yes,
is a
okay, but
paramagnet,
I'll,
what is spin liquid.
explain this, yeah.
So it's a two-dimensional diagram of the parameters that, characterize this particular system. And then for each point, there is a type of behavior of the material. And it turns out that there are sort of different phases that behave very differently.
Yeah, they are classified.
Okay.
You can
Mhm.
classify to different phases.
Here about distinguishing between where are we in the graph.
Excellent. Okay, excellent. So our first test as condensed matter physicists is to classify. You have to tell me this is water, this is ice, this is vapor, or this is a ferromagnet, a paramagnet, a spin liquid. That's the first task. The second task is to understand how do you switch between them. What's happening along those boundary lines. Okay, so this is the second task. If you completed both of them, you're happy. Okay, so this is our approach. Okay, good. Okay, so we like examples. Okay, so this is sort of the spherical cow of this problem. Okay, so this is there's always a joke that physicists see everything as a subclass of the Ising model, right? This is what they think about. I think it's true, but maybe it's a religion. So okay, so this is the spherical cow of classical statistical mechanics, and writing on phase diagrams, and it's a classical model of bits, again, not of qubits, and and it has the following Hamiltonian. Okay, so because I switched to the Ising model, sometimes, I apologize, I will call qubit spins, but hopefully this dictionary would help. I identify 0 by a spin that points up and 1 by a spin that points down. Okay? So what is the Ising model? So the first thing we need to give are what are the degrees of freedom. So we have some array. It could be 2-dimensional, 1-dimensional, 3-dimensional, different lattice geometry. It matters, but not for our discussion. And on the side of this lattice, we'll place our degrees of freedom, our bits. Okay? And this particular configuration can be encoded. Let's say if you want to call this a code word, it could be like 0, 0, 1, 1, 1, 0, etc. Okay, so we have a state of bits. And now, I'm doing physics, so I need to give an energy penalty for this state of bits. Okay, so how do I count it? I have this formula here. Okay, so I'm running over all nearest neighbors. Okay, and I'm asking if they align in the same direction or they anti-align. Okay, and if they align in the same direction, I get a reward. I lower my energy with a value j. Okay, because z times z would be 1, and I get a minus j. Okay, and if they are anti-parallel, okay, I get a penalty. Okay, the energy cost would be plus j. Okay, so those are the rules of the game. This part here basically tells you if the spins align or do not align according to this external field. Okay, so if they align or they point up, I'll get an energy h. If they anti-align with the external field or point down, I'll get a minus h.
What is the subscript?
This one or this one? I? H. J.
HZ.
J.
It's just a parameter.
This is a constant. It's a number.
And what is H?
It's a number too.
It's a single number?
It's a single number. Yeah.
So why do you have a subscript?
Because it's related to. Later on, there would be hx. Okay? And you can imagine this would involve quantum mechanics because z and h do not commute. Okay? Good. Okay, so now the most important part, if you want, the only take-home message you want to do here. So there was a very smart physicist known Landau, and what Landau told us that the first thing you need to do when you look at those problems, you look for the symmetries of the problem. Okay, so so when we take the external field to 0, when h goes to 0, we have a symmetry in the problem. What is the symmetry? The symmetry is to take all the spins in the problem and flip them. Okay, if we take zi to minus zi, so we have this mathematical notation here, then the energy remains the same. Okay, because we have a product of two z's, so minus 1 squared is 1. Okay, good. So this is actually the most important sentence in all my slides. So please remember this. Okay, so. So we want to compute the statistical mechanics of this problem. We would like to compute the Gibbs distribution. So, so I have an exclamation mark. So this is a very challenging computational task. Okay, naively at least, it would require you to sum over 2 to the n summands. You have to go over all the states, okay, and sum over the Boltzmann rate. In reality, it's actually, we have smart stochastic methods to tackle this, so it's actually, it has complexity classes. If you want to be purist, it's a polynomial problem. Okay, you can run the same Markov chain Monte Carlo we looked before, but it's a naive brute force calculation would tell you that this is, yes? So, so the partition function z is the sum over all possible spin configuration, e to the minus beta, the energy of this specific spin configuration. Okay, so the number of spin configuration goes as 2 to the n. So you would have to sum over 2 to the n factors. Okay, this is the partition function. Okay. It's a normalization. So I said before, although it looks like just a normalization, actually, if you know how to compute this, it's a, okay, formally in probabilities, it's actually a generating function. If you know how to compute this, you take derivative of it and you can basically know almost everything. Okay?
So you have temperature here, and you want to find the state that you found before, the low. That's what you're trying to do.
Yes.
Now more complicated. When
Yes.
you're trying to find this low thermal, you find yourself trying to compute the partition function, and that is complicated.
Yes, right. Before it was simple. We had just a single qubit, so it was very simple to do this. Here, that's a very challenging task.
And you just want to approximate the sum.
I will approximate it in a second. Okay?
So I'm just confused of how what you explained here is related to what you explained in the previous slide.
Which one? This one?
No, I mean like
The philosophy one?
yeah, that's the one.
Okay, so if I can compute the partition function, okay, okay, in a second you would see that actually this model would have two distinct phases, and then it might be clear. So let's watch one slide. If it's still unclear, then we'll see. Okay, good. Okay, so so I would like to give you an intuition, okay, to what to expect that we'll see. Okay, so this is a really nice exercise that you would do in your homework 4. Okay, I strongly encourage you to do that. Instead of thinking about the Gibbs distribution, we can define a new object, okay, which is known as the free energy, okay? And the state of the system would be uniquely determined by this object. Okay, let me explain what this object means. Okay, so the object is a sum of two terms. The first term is the energy, which we already know, okay? The second term is the temperature times a new object, which we call the entropy. Okay, so what is the entropy? The entropy is defined as follows. It's minus sum over all your configuration, the probability for this configuration times log of the probability. So what do you need to know about the entropy? In order to maximize the entropy, okay, you need to, as we say in here, you need as much balagan as possible. Okay, you need as random as possible. For instance, if you think about some discrete probability, what is the most entropic probability that you can write? A uniform, okay? It would be the less informative. It would tell you nothing about the system, okay? So we see that basically if we try to minimize the free energy here, you basically have a competition. Why? Because when the temperature is vanishing, 0, to minimize the free energy, what you would like to do is to minimize the energy. But when the temperature is very large, you would like to minimize the second term. The second term has a minus sign, so you would like to maximize the entropy. So, okay, so 99% of statistical mechanics really deals with this competition between energy and entropy. Okay, so let's try to understand how this would materialize in the Ising model. Okay, so when we go to very low temperatures, okay, we said that we would like to minimize the energy. What does it mean to minimize the energy? Okay, I remind you, so to minimize the energy, we want all the spins to align in the same direction. Okay? Or, okay, so
All neighboring spin.
So unfortunately, you are not correct.
No.
I would like to have all the spins to align. And the magic here, and you are correct in the sense that the penalties that the Hamiltonian gives me is only on neighboring spins. Okay, but this is maybe the first time you see collective phenomena. So what happens, because this one wants to align with this neighbor, also the neighbor wants to align with this one, etc., etc. Okay, so to globally minimize the energy, we would like to all of them to point in the same direction. And now we have a problem. Okay, because I told you that the Hamiltonian has a symmetry, right? So they can all point up or they can all point down. Okay, so what happens in nature, you get a spontaneous breaking in symmetry. It's enough that you have a very tiny field that would align all of them up or all of them down. Okay, so this is a broken symmetry phase known as a ferromagnet, where all the spins point in the same direction. So now let's go to the other case. Yes.
Why won't you just have a distribution equal distribution between this and this?
So you will have. This is, so formally, you're right. So the distribution is an equal probability sum over the two. Okay? Right. But physically, this is not what's happening. Okay? What's happening physically is that the energy barrier to go between all up and all down is humongous. It grows exponentially with the system size. And what's happening physically is that it would take you the time of the universe to tunnel or to move from one to the other. So the magnet, it's an unstable point. Okay, you would collapse to one of those. Yeah. Well, what's happening in a magnet? When you take a magnet, it picks a direction, right? Well, what maybe?
I have a question that I don't understand. What do you mean by the Gibbs distribution minimizes the free energy? In what sense does it minimize it?
So that's the exercise. Okay, so among all possible distributions, so let's say you compute this. This f of rho is a function of the distribution. I tell you, pick any distribution that you want. Okay, so if you try to minimize this among all possible distribution functions,
Okay,
the Gibbs distribution would be the one that would minimize
then the
this.
entropy is the entropy of the distribution, and
yes.
the energy is the expected energy in the.
In this specific one. This is a one-line calculation, which is very nice. I encourage you to do that. I'll post the solutions online. Or you can ask Jiminy. It also knows how to do that, apparently. Okay, good. I think I'm way over time, no? So maybe
Yes,
I can...
maybe you can
yeah.
take 2-3 minutes to wrap up.
Okay.
Maybe just to say the
Yeah.
phase turn, the
Okay.
phase diagram, or.
So maybe, okay. So, okay. That was pretty optimistic. Okay. In the remaining minutes, we'll... okay.
But do you want?
Okay, I just want to finish with the phase diagram. Okay, so I promise you that I'll plot you a phase diagram. Okay, and what I would like to mention here are two things. The first thing is that I think we slightly discussed about this phase transition as a function of temperature. We go between balagan or a paramagnet and a ferromagnet. But what I would like to highlight, and this is I think more related to what we do here in quantum computers, is actually a phase diagram that happens precisely at 0 temperature. Okay, and this is kind of a miracle because I told you that everything freezes up at 0 temperature. Okay, so basically you would imagine that everything would be a ferromagnet. Why try to minimize the energy? But it turns out that you can change the role of thermal fluctuations with quantum fluctuations. Okay, if that quantum fluctuations are strong enough, okay, due to non-commuting of operators, they can precisely play the role of thermal fluctuations and actually give you a quantum paramagnet. Okay, so this is my main thing, and okay, let's finish here.
Were we supposed to understand this, the last thing?
What?
Were we supposed to understand the last sentence?
So no, not at all. But
Okay.
the lecture notes are online, so you can ask me, and I do a full. So remember the formula I told you in the beginning was this A dot R. So this is all you need to know to look at quantum phase transition. It's written in this slide, so you don't need many slides for it. Okay. Good. Okay. Thanks.
שתיים, נכון?